Okay, so welcome to the final review for Blueprint. This is going over basically everything that we went over in class today, which was going over most of what we've gone over in terms of what's going to actually be on the final itself. So let's just get going. Sorry. So, low voltage control and relays. Low voltage controls are mostly used for lighting, at least this is how we use them. They are achieved by using a transformer to transform 120 volts to 24 volts to power switches and relays that then output 120 volts to lights. So, low voltage switches tend to be 2-button single pole double throw, and relays are normally single pole single throw, at least based on what we've had in lab. Diodes are used to control the flow of current, which allows you to have master switches, which can override other switches and prevent power from going back to the transformer. So, for example, in the low voltage job sheet, we use the master switch to power lights 2 and 3 without their respective switches affecting the other's light. Um, and normally, at least on the diagrams that we have used, your black wire is your power off, your red wire is your power on. I believe that the white wire is the power to the switch, and the blue wire. Oh, sorry. The white wire is power to the relay, I believe, and the blue wire is power to the switch. I might have that mixed up. Yeah, my apologies if it's wrong. Um, Chapter 1 was over bidding and code layout, so a couple different pieces of paperwork to know are the notice to bidders, which sets out the rules of the bidding process. The general conditions is the layout for the rules for everybody involved, including the owner, the builders, and the architect sometimes. An agreement is a document confirming that all parties agree to laid out plans and rules, and proposals are pitches by the contractors or subcontractors to show to the building owner or the main contractor to get their bid approved and get the job. So, the code layout. The NEC is laid out in 9 chapters as of 2026 and will be changed in 2029 to be a bunch more chapters. And the code is updated every 3 years. Now, listing is performed by groups like Underwriters Lab, the UL logo that you see on a lot of devices. It acts as a certification saying that this product has been tested to be safe when used under specific conditions. Labeling is the mark on the device that displays that it is listed, and approved means the device is approved by your AHG for use in their jurisdiction when used for listed purposes. Okay. Chapter 13. This is one of the big ones. So, transformers and services. Transformers come in single phase or 3-phase setups, dry type or oil filled, and pole mount or pad mount. Oil filled transformers, their oil is used to help insulate the wires and to cool the wires and components within them. Pad mount transformers are the green boxes you'll see on the ground a lot of the time, and pole mount are the tubs that you'll see on the electrical poles themselves that you'll see towards older buildings or buildings where not a lot of power is run underground, like in the country, for example. So, single phase versus 3-phase. This is important to remember. So, single phase is electrical power provided by only one or two hot conductors that are 180 degrees out of phase with each other. So, for example, if you're doing single phase 120, you have one hot conductor, so you don't have to worry about that. And with two conductors, normally they should be 180 degrees out of phase with each other, I believe. I'm pretty certain that's right. 3-phase is when power is provided by 3 separate hot conductors that are each out of phase or slightly delayed from one another, so that you are always being provided with a rough average amount of power, which is what we've been going over in AC. When calculating using 3-phase, you need to use the square root of 3 or that 1.732. So, for example, when finding the amount of current that a device is going to require, you would take its kVA or kW rating, you would divide that by the voltage that it's going to use, and then by 1.732 if it's a three-phase device to find how many amps it's specifically going to take. You should really know this if you did the single-phase, three-phase job sheet, which I think most of us did. It was a really good help, but yeah. To find your values, you just use Ohm's law. The P equals I times E, watts equals volts times amps. kVA is the same as watts when we're talking about like calculations and shit. Yeah. Transformer connections. Transformers come in two different connection configurations. And they have 3 or 4 different voltage ratings and are either 3-wire circuits or 4-wire circuits depending on if they have a neutral. So the two connection configurations are delta, which is shaped like a triangle, and Y, which is shaped like the letter Y. The most common voltage ratings are 12240 delta, 12208 Y, 277 480 Y, and 265 460 Y. The 460 is a bit rare, but yeah. Delta transformers are normally hooked up in series, and Y are normally hooked up in parallel. This is why in 12240 delta, your B phase is a higher voltage to ground, because you're picking up the voltage from the phase itself and half from another phase. And this is referred to as a wild leg and must be marked orange to inform people that it is a different voltage from your other conductors. So, open and closed deltas. Closed deltas are what is most common, where it's a complete triangle, but you may see open deltas where 2 of the 3 phases are not connected to each other. So for example, it's a triangle missing one of its sides. This allows the utility to provide 3-phase power with only 2 transformers while still allowing another transformer to be added in the future if the demand is needed. 3-bank open deltas only provide 57.7% the amount of kVA per phase. So for example, if your total comes out to 300 kVA, your 3-bank open delta is only going to provide 57.7% of it. With a 2-bank, it's going to do 86.6%, which would come out to the same amount as long as your transformer legs are all the same value. So for example, 300,000 volt amps, 300 kVA at 57.7 is equivalent to 200 kVA at 86.6, I believe, is the calculation that we did for that. Current transformers are transformers used to decrease the amount of current going through a meter. So this is used when a meter may not be able to handle all the current going through it. I think about 400 or 800 amps. So the current is reduced by a certain factor. This allows the meter to operate safely without actually reducing the total current. So basically what it's doing is a CT is only monitoring part of the current. It's taking a reduced load. So for example, it can reduce 400 amps down to 200 amps, and then for each amp you would multiply by 2. So if you're reading 200 amps on a CT with a factor of 2, then it would actually be 400 amps. That's my understanding of how it would be described. Grounding and bonding. This is another big one, and we get a lot into it next semester, so I did it about as simply as I could. So, bonding is the act of connecting all metal parts of a system together to create a path for current during a fault. Grounding is the act of connecting a system to earth to provide a low impedance path to dissipate current. The grounding electrode conductors are used to create a point for the system to connect to the earth, and are commonly concrete encased electrodes, pieces of concrete or rebar in concrete, grounding electrodes, etc. Equipment grounding conductors are used to connect the devices themselves and parts of a system to the entire system. That's why you need to ground your devices and ground your box so that it's actually connected to the system. And your main bonding jumpers are used at the service to connect the neutral and the equipment ground to be able to trip the main breaker during a fault. Because if you didn't have it, if a ground fault were to occur, you're not going to get enough amps through your grounding electrode conductor to trip your breaker, is the explanation that I read. And I think that makes pretty decent sense. That's why you have that bar connecting your neutral and your ground. Okay. Working symbols and drawings. We should know this by now. We did these in Residential Blueprint. It's pretty damn simple. You have duplex 240 volt lights, split wires, wall lights, single pole, three-way, four-way, pilot light, GFCI, AFCI, etc., etc. You guys get the point. Hopefully, this should be pretty easy. Conductors and ampacity. So just going over the letters in the conductors, T stands for thermoplastic, 2 H's is 90 degrees rated, 1 H is 75 degrees rated, and no H is 60 degrees rated. X stands for thermoset or rubber. You'd also see R sometimes, but R is an older one, I believe. N stands for nylon jacketed, and W is rated for wet locations. And if a conductor has -2, it means it's dual rated for wet locations and for 90 degrees. So, for example, the wire that we use down in the lab is THHN-2. So, for 1 gauge and below, you use the 60-degree column for devices and breakers. And for 4 out and above, you use the 75-degree column. So, ampacity correction is correcting the ampacity of a wire based on temperature and insulation rating, as well as the amount of wires in a raceway. So conduit correction only applies if the raceway is longer than 24 inches and only starts really affecting ampacity once you hit 10 or more conductors, at which point your factor becomes 50%, compared to if it's like 4 to 9, for example. I think it's like 80% still, so not going to affect it too much, but yeah. Temperature correction is based on the ambient temperature of the location and is one time you would use the insulation rating for the wire. So, for example, if you're running THHN wire and you're running it through a hot location, you would use the 90-degree column in this case specifically. One thing to note that is not on here, the ambient temperature is based on, I think, about 30 degrees Celsius, which I think comes out to about 80-something Fahrenheit. If your temperature goes below that, you don't start rating your conductor for more amps than it's rated for already. It only applies if you're going above above your standard ambient temperature. Rooftop runs of wire at an extra 60 degrees unless the wire is XHHW. I don't think it applies to XHHW2 or W-2. I think it's just the XHHW. So, wires on a raceway. The conductors you count for ampacity correction are called current carrying conductors, which are the conductors that can be expected to be carrying current at any one time, which normally means the hot and neutral conductors of a circuit. In a circuit with a three-way switch, only one traveler between your 3 and 4 ways is counted because you won't have both travelers carrying current at the same time unless your circuit is malfunctioning. In a multi-wire branch circuit, you would not count your neutral conductor, as the neutral conductor is only used to carry the unbalanced load between your 2 hot conductors. The other thing is your equipment ground conductor is also not current carrying, because if your equipment ground is carrying current, that generally means that you have a ground fault. Okay. Calculations. This one we didn't have much to go over. So when calculating the VA of a building, you would count 180 VA per yoke of a device. A duplex receptacle is on 1 yoke and is 180 VA, and a single receptacle is on 1 yoke and is therefore 180 VA as well. So the best way that I can explain this is 1 yoke is essentially 1 space in a box. So a handy box has 1 space for 1 outlet, and a 4 square has 2 spaces for outlets. So therefore, a box with 2 duplex receptacles, a 4 square, would be 360 VA then. Yeah, like I said, this was basically all that we talked about at the end of class there, or not at the end of class, but during class today when we were reviewing everything. There's probably more to this, but Troy didn't see any purpose in talking over the rest of it, so I don't know how much is really going to be on the test. Okay, cord and plug connections. Devices and plugs must adhere to NEMA configurations. Devices and faceplates may have certain markings. The big 2 that we talked about are the orange triangle, which denotes that it has a separate ground that terminates at the main panel to reduce electrical noise, so that way it doesn't trip out with the rest of the conductors if there was a ground fault. And a green triangle identifies that a device is hospital grade. I think that might be reversed, but that's what Troy said in class, so you might want to double check that. Chapter 9, Special Systems in Wire Mold. Pretty simple. It just went over fire alarms and stuff, but wire mold is the big thing. Special type of raceway. Splices can be done in wire mold if it has a removable cover. It can be ran through walls if it is unbroken the whole length and the conductors are not exposed to air. And multi-outlet assemblies, like what people were setting up, the plug mold, are counted as wire mold. Okay. Lights and lighting. So lights generally fall under two categories: your general usage lights or your HID, high intensity discharge. Your general use is your LEDs, your fluorescents, and your incandescents. That's what you're mostly going to see in a house. HID lights are high pressure sodium, mercury halide, and metal halide, I believe. I'm not sure. High pressure sodium are the main type of HID used today because they're the most effective and they are orange in color. LEDs are the most efficient lights, incandescent are the least efficient, and fluorescent lights usually require a ballast. Okay. Normally, can lights need to be 3 inches from insulation, but if they're rated IC, they can be touching the insulation. IC meaning in contact, essentially. Can lights also need to be half an inch from combustible materials like wood. Special ballasts are required if you want to dim them and require manual disconnect either at the ballast itself or as a switch. The lighting color of lights is rated in Kelvin, where the higher the number, the bluer and the whiter it gets. And lighting efficacy is the lumens provided per watt consumed, and lumens are measured in foot candles. Essentially, your lumens are your current and your foot candles are your amps. Alright, lighting in closets. Lights are not required in closets, but have very specific rules if they are installed. LED and incandescent bulbs need to be 12 inches from combustible material if surface mounted, 6 inches if recessed, and cannot be in the open air. Fluorescent lights are always 6 inches from combustible material, period, and pendant lighting cannot be used in closets. Emergency power and systems. Again, this is one that we didn't talk about too much today, but the most common form of emergency power is a standard generator. Generators need to be sized to the load that would be connected to them in the event of an emergency, and they need to be prevented from feeding power into the service side, because if you were to accidentally do that, if a lineman were to go and work on a service that he thinks is dead, then he might get really hurt. Alright, overcurrent protection. Fuses are usually single use, but often very cheap and often fast and open faster depending on the current going through them. They have no limit to how fast they open. The speed at which they open is dependent on the amount of current going through it at one time. Breakers are able to be reset very easily, just the switch on them, but are limited in the speed at which they open because they're mechanical. Some fuses contain sand to extinguish the arcs that happen in them. Breakers are usually mechanical plastic mold breakers like you would see in a house, but now there are solid state digital breakers as well, which I believe act faster and just have less moving parts. And fuses come in a lot of different classes, which I go over here. So Class H is the cheapest fuse. It has a 10K minimum current interrupting rating. Class J has a minimum of 200K interrupting rating. Class RK fuses are used for motor protection. Class S fuses are only for 120 volts up to 30 amps and require adapters to be put into Edison base sockets. Class H and S fuses are the only non-current limiting fuses. Everything else is current limiting. Fuses come in various amp ratings, but often a smaller fuse can get adapters to fit in larger sockets, but not vice versa. That means that the fuse will trip before what the disconnect is actually rated for, but that may be useful in certain situations. But manual disconnect switches, they're the large boxes that you see with the big red arms that you pull down to disconnect the power. You'll usually see them like as part of MCCs, wherever you just need an emergency disconnect. That's your most common form. Standard sizes for them are 30, 60, 100, and 200 amps. And you must always size your disconnect larger than the load that's going to be connected to it. So if you have a 31 amp load, you need a 60 amp disconnect switch. Cable limiters. So the cable limiters are connected directly to the conductors themselves. They're not overcurrent protection. This is one that I think tripped a lot of people up on the test, just kind of due to the nature of when we talked about it. But cable limiters are used to protect the circuit against faults by isolating faulted conductors to try and stop the problem spreading. So, for example, if you have a cable that is currently dealing with an arc, it would isolate it, bring it away from other cables essentially, or cut the power to specifically that one. I'm not exactly sure how it works, but that's the simplest way to explain it. Then just some miscellaneous information that I didn't fit anywhere else. Show windows are rated at 200 VA per foot, and multi-outlet assemblies are 180 VA per 5 feet, and only 180 VA per foot if under heavy use. So if you have a lot of things plugged in, think of like, a cafe during finals, you may have like 5 or 6 people on a laptop at a time. Maybe not a heavy load, but at the same time, probably worth calculating it at that point. Obviously, that's something that usually your engineer is going to do, or your journeyman, but, helpful to know, I guess. But, yeah, that's all. Yeah, finals are tomorrow. If you need me, I should hopefully be there before 9 o'clock to talk over things. And I will see you guys tomorrow. Have a good night.